Okay, I'm doing a few more problems to help y'all get ready for the unit test on linear, exponential, and quadratic functions. So I'm turning the video off and focusing on this work. So starting with linear functions graphically, I'm going to just work with the medium ones. I designed the medium to be a little bit tougher, but it's still the equation of a line. With g of x, as soon as I see that linear or that line, I know linear function. So I'm writing out y equals mx plus b. Because that helps me remember, hey, I need my m, which is the change in y divided by the change in x. Or when we look graphically, rise divided by run, just keep in mind that you have to use clear points to make your life easy. That's down 3. That's to the right 2. So my slope is -3/2. Always want to remember my b is my y-intercept, and my y-intercept is 0, 4. Yep, 0, 4. And so my equation for g of x is -3/2 x plus 4. Now moving on to f of x. I recognize that beautiful exponential curve. So I know I'm going with the exponential equation, a times b to the x. Now, keep in mind, these equations are literally built out of what is happening in the function, right? In a linear function, a constant additive rate of change. And so the m is being multiplied by x because that multiplication indicates repeated addition with just the y-intercept being added. That is actually why my favorite form of a linear equation is a plus bx, that's still indicating, in this case, a is my y-intercept, repeatedly adding b, which is why it's multiplied by x. And so that b acts as my slope there. But moving back to this exponential, notice that previous linear actually mirrors the exponential equation really well. But in this case, again, a is y-intercept. There's just one of those a's. I see my y-intercept at 0, 6. So a is 6 times. Now, the thing I need to always remind students is so often students try to do rise divided by run here. So down 3 and to the right 1. But if you look at the next point, it's not down 3 to the right 1. We cannot use the idea of slope for an exponential function. What we have to use is the constant factor. You can actually see the constant factor in the table or in the graph, but I would highly recommend identifying a few points, creating a table, because it's going to make it easier to find that constant rate of change. Now, some students may just naturally notice that it's times 2/3. That's not the norm, though. And so what I recommend, a way to always identify the constant factor, is we are literally multiplying by the factor. If I take 9 and I multiply it by my factor, I get 6. If I take 6 and I multiply it by my factor, then I get 4. And so I can solve either of those equations. I like to use the reciprocal. 9 divided by 9 is 1. 1/9 of 6, it will be 2/3. The same would have been true for that second equation. And yes, you can just divide. I use the reciprocal because by definition, the reciprocal is actually the inverse, inverse, just the multiplicative inverse. That's the word I'm looking for. But also it helps tie in to a few other ideas that we'll study. So b is 2/3. There's my equation. If I'm trying to create a graph, personally, I'm always going to make a table to help me get there. Now, I will say, some of us may be very adept with this function and just be comfortable saying, hey, there's a y-intercept of 4. That would be very important to note. and then a constant factor of 2, which again, I would use that in a table. And so if I start at 4 and I multiply it by 2, I get 8. So 1, 8. Now, if I go backwards, -1 was mapped to 2, -2 mapped to 1, -3 then would have been 1/2. That way, when I multiply by 2 each time, I get the next point. Again, if I was doing a table, though, a couple of things with the table that are really beneficial. You just get to choose your inputs and you substitute those in. I always start with that 0. So 2 to the 0. You can just type it into a calculator, but 4 times 1 is 4, just like the y-intercept I had graphically. If I type in that 1 or input that 1, 4 times 2 is 8. If I input that 2, 2 squared is 4, 4 times 4 is 16, and so I could have kept that going. I can also input that -1. And we talked about this pretty heavily in class. Don't forget, a negative exponent just tells me how many times to divide. Positive exponent, how many times to multiply. Negative exponent, how many times to divide. So now I'm dividing by 2 twice, right? And so notice I've got my input of 0, output of 4, input of 1, output of 8, input of 2, output of 16. Input of -1, output of 2, input of -2, output of 1. And that shows the same pattern that I could have found and just use that constant factor to get multiple of those points. So that's graphically that exponential function. Same thing with y equals 3x plus 2. Now, linear are usually typically easier for students. You've been doing it since, I think, 7th grade, 6th grade, something like that. We just want to remember it's the slope there is change in y divided by change in x. So 3 divided by 1 with a y-intercept of 2. But once again, please feel free to take the time to, so it's going up 1, 2, 3 to the right 1. Or you could even go down 1, 2, 3 to the left 1. But there's the equation or the graph of that linear function. But again, you can always make a table. You can always do inputs and outputs. If I input 0 for x, 3 times 0 is 0. 0 plus 2 is 2. If I input -1 for x, 3 times -1 is -3. -3 plus 2 is -1. Notice those points perfectly match what I have on the graph. Input of 1, 3 times 1 is 3. 3 plus 2 is 5. Same exact story. Okay. And if you look down here, those are the answers I already put. Except apparently I changed that equation for the spicy, so my bad. I'll have to update that for next year's. Okay. Same thing, mild here, or going with medium. Now, just looking at these two, when I look at the right-hand table, I immediately notice fractions that start to pop up. So I'm thinking it's an exponential, which means this leftmost one, more than likely, has a constant additive rate of change. Remember, your rate of change is the easiest way to identify the type of function in a table, right? Change in y divided by change in x, because it's additive. This is a linear function. I don't have the y. Well, as soon as I know constant additive, I know this is linear. And so I write out that equation, mx, f of x equals mx plus b. Just found my m by doing the change in y divided by change in x. And I still need the y-intercept. Remember, all y-intercepts, the input is 0. So I do -2 plus 2, and that gets me to my 0. So I have to continue subtracting on the y's. But there's my y-intercept. Or 3 is my b. All right, there's my equation for that line. Once again, don't forget, you can always just make a table or make a graph of that table. You use whichever representation is the most comfortable for you. Now with this exponential, I got a times b to the x. Now, technically, I need to find that constant factor, but again, these values down here are really indicating it's probably an exponential, but I don't know the factor yet. So times f, multiplying by that constant factor. That's the whole idea of constant. It stays the same factor I'm multiplying. So 9 times f is equal to 12. Use your reciprocal. 9 divided by 9 is 1. 12 divided by 9, they both have a factor of 3. So 12 divided by 3 is 4. 9 divided by 3 is 3. So my factor is 4/3. And that actually makes a lot of sense when I look here at this section, because I literally have a divided by 3, and 16 times 4 is 64. So my constant factor is 4/3. And I don't have to do any extra work this time to find my y-intercept. That y-intercept is 12. And so 12 times 4/3 to the x. The spicy, this is something we still actually need to be able to do, but just creating a table. I did make this, this came after the graphical because I wanted some spicier numbers. And so the reality is if I'm creating a table here, I know how this function works. And so I know my y-intercept is 0, 4. I know when I go to my first term, I'm going to multiply by 3 halves because that's my constant factor, which gives me 6. Multiply by 3 halves again because that's my constant factor. That gives me 9. And I can just keep this going all day. Got my constant factor. It's going to work out nicely. I can also go backwards by just multiplying by the reciprocal. That is part of the reason why I use the reciprocal so often, because when I do 4 times 2/3, the multiplicative inverse, I get 8/3. When I multiply that by 2/3, I get 16/9. And so I know that I have those values correct. But at the end of the day, if you want, I would highly recommend taking advantage of a function or any relation is the idea of inputs mapping to outputs. So if I type in -1, or I let -1 be my input, so x is -1. Once again, we talked about this earlier, both in class and just here. Negative exponent indicates division. So I'm going to multiply by the reciprocal to divide by that fraction. 4 times 2 is 8. And 8 divided by 3. And that perfectly matches what I have here. If I had wanted to jump straight to f of 2, input of 2, so x is 3 halves, no, x is 2, so 3 halves to the second. To square a fraction, honestly, you can just see it as it times itself. And so 3 times 3 is 9, 2 times 2 is 4, 4 divided by 4 is 1, so f of 2 is 9, exactly what I have here. So don't be afraid to just use inputs and outputs, and that's it. I'm going to leave you to do inputs and outputs with the second one. I will note that in the second one, I'm dividing by 3. So I'm going to make sure that my inputs are multiples of 3. That's just me, because I don't want to make things hard. But if I'm making this table, I know that this is my slope. Remember, multiplication is repeated addition, and slope is the name of that constant additive rate of change. So if -4/3 is my slope, 8 is my y-intercept. And then from there, I am subtracting 4 from the y, right? Remember, change in y divided by change in x. Subtracting 4 from the y, adding 3 to the x. And then I can do the reverse to go backwards. Okay, there's my table. If you substitute those inputs in, you get those outputs out. And again, notice I ended up going by 3s because division by 3. All right, last little bit. I am hopeful that we are all good on these, but this is the last little section. Figured I might as well end it well. I see a parabola here. As soon as I see a parabola, I know this is a quadratic, and I know it's a function. A quadratic, well, not all parabolas create quadratic functions, but I know it's a function because that vertical line test. That vertical line is showing me each input is mapping to only one output. That is why the vertical line is only intersecting the graph once. That's in direct contrast to if I look at this function right here, that one input is mapping to three different outputs. So this is not a function. It is still a relation. It's a mapping of inputs to outputs, but it is not a function. We haven't studied this one. I didn't actually mean to leave that equation in there, but you can literally see a variable in the exponent. This is an exponential function because of the name of that. Well, not because of that curve, but the name of that curve is literally an exponential curve. That's how I know it's an exponential function. Again, the variable in the exponent is also a key detail. But when we get to tables, you got to keep in mind with a table, we need a rate of change or make a graph. You could always make a graph. I'm not going to, because when I look at this first table, 16 times 2 is 32 divided by 3. And so I'm instantly wondering, is that my constant factor? And so if I do 36 divided by 3, I get 12. 12 times 2 is 24. So my constant factor is 2/3. So this is an exponential. It's got a constant factor of 2/3. Now, again, you could have taken that good old strategy of 16, or I was going to do 24 times my factor equals the next value of 16. Use that reciprocal. And so it does come out to be 2/3, right? So same strategy as before. As soon as I look at number, for the second one here, I was thinking not a function, but I just noticed that -5 just is mapping to 27 twice. Okay. So it's still not a function, but it's not because of the -5. The -5 is actually still mapping to the same value, so that's okay. But -3 mapping to 14 and -3 mapping to -18, that means one input is mapping to two outputs. This is not a function. So every function, each input maps to one and only one output. As soon as I have that one input mapping to two outputs, not a function. Next one, +6, +6, +6. I just noticed that constant additive rate of change. And it's constant additive on this side as well. So this is going to be a linear function due to that constant additive rate of change. And it is also a function. Each input maps to one and only one output. Moving on to the second one. Each input's mapping to one and only one output. I start trying to think about the type of function. My guess is it's got two roots right there, right? The output is 0, probably a quadratic. Let's see what this rate of change is looking like. So definitely not constant there, but this is constant additive, right? And the function we studied already that has a constant additive rate of change is a linear. So this adding and subtracting this rate of change is a linear additive rate of change, and that means this is a quadratic function. Just identifying if the relation is a function, I immediately notice a times b to the x. That's exponential. It's constantly, repeatedly multiplying by 3/2. You can even check it. Each input is going to get a unique output. Next one. This is something we've studied more since I gave this to you, but that square there tells me quadratic. In fact, this is the vertex form of a quadratic. And remember, quadratics that we are studying are functions. So this is a quadratic function. If you graph it, it's going to look something like 1, 2, 3, 2, 4, 6, 8. So I'm going by 2's on the y, 1's on the x, but boom and bop. Right? Correct vertex, concave down. That's a function. Issue here, y squared equals x squared plus minus 7. If there's just y equals x squared minus 7, it'd be quadratic. We're going to talk about this more next unit. But if I take a square root right here, well, first off, if I just graph this, it's going to give me a funky looking graph. I don't even know off the top of my head what it would look like. I think it's going to be what we call a hyperbola. Don't stress that. We're not studying that. But, sorry, long day of teaching. Because I took that square root, I'm going to need a positive and a negative there. I'm going to say that more heavily next unit when we solve quadratic equations. But that means each input of x is going to have a positive and a negative. So it's going to have two outputs, so not a function. This next equation may be very tempting to look at it as a quadratic, but I have no square there. I have the highest thing I have is a simple multiplication. And so I can distribute that negative 4/3. And if I do, I'm going to end up with, so I'm just simplifying, a linear function, right? So it was linear originally, but it's easier to see now. You can, again, also just graph this to see that it's linear. We study this more heavily since then. Again, this is a linear times a linear. This is the idea of a quadratic and quadratics. Oh, and so again, linear function, quadratic function. Please feel free on the actual test, if it's the calculator portion, to graph those equations, but be aware this is probably going to be on the non-calculator portion. 14, you can make a table. He keeps going half the distance, so repeatedly multiplying by a half. Each input's going to have one unique output, and it's going to have a constant multiplicative rate of change for an exponential function. This next one is actually pretty interesting. You've got 50 M&Ms. You want to make the largest parallelogram possible with the candy. This actually ties into the Gold Rush task we did. So if you think about the fact that you're going to have candy, and you want to maximize the size, what you're talking about is the area. And this is not going to be 50. I'm just kind of giving an example. And so in that case, we're going to have a base times a height. Both of those are variables. Both of those are going to be linear variables, right? And so a linear times a linear is going to give me a quadratic in x squared. And it'd be a quadratic function. All right. Hopefully that was helpful for some of y'all trying to master these equations a little bit better. I will, as soon as this finishes converting to a video, I will upload it to YouTube.